Good morning. All right. So we're going to finish up the natural exponential function section. We've got like one more example to do there and another formula to look at. And then after that, we'll move on to the next section. Just a couple of reminders. Don't forget the test is due by midnight tonight. So if you have not submitted that already, just make sure you get that done and get it uploaded before midnight tonight. If you have any questions or issues uploading, please let me know so that I can address those. Please try to do it before 11 o'clock tonight or so if you think you might have issues uploading it, because I probably won't be on to answer those questions if you run into issues. So again, if at least try to know what you're doing, so that you're not sitting there at 11:59 tonight trying to get it uploaded and then run into issues. Okay. Any questions, comments, concerns right now before we get started today? All right, and then the other thing would be that the next homework assignment is due right now tomorrow night. We'll see how far we get today. I might still push it back another day. And then also don't forget that Friday and Monday are still holidays for us. So we will not have class on Friday of this week or Monday of next week. Okay, so you'll have a 4-day weekend over the weekend this weekend. All right. So getting back into the natural exponential function. Okay, so we got through a lot of this. But the next thing we want to look at is our continuously compounded interest formula. So if you remember in the last section, we looked at compounded interest and we had a formula that we used for that. But now this is what we call continuously compounded interest instead. So if you see in your problem that your interest is compounded continuously instead of something like monthly or daily or annually, those keywords, right? If it says continuously instead, this is the formula we're going to have to use now, right? And notice we have this E, that's that number E that we've seen before in this section. So we still have our principal, that's our p-value. We have our E, we have our rate, which is still going to be a decimal, and we have our time, which is still in years. But notice there is no N value anymore because our N, right, the number of times we're compounding continuously, so it's an infinite number of times, which is why we're going to use this E instead now, okay? So you might see that referred to as PERT, right? P times E to the RT, the RT being in the exponent here. So I'll give you a chance to get that formula down because we're going to use it on the next slide. All right, does anybody need more time to get any of that now? All right. So let's take a look at this one. So we want to find the amount after 3 years if $1,000 is invested at an interest rate of 12% per year, compounded continuously this time. All right, so since we see the keyword continuously, we know we're going to use that formula from the last slide. What are we going to start with this time? Good. So our p-value is going to be 1,000. So that's our principal. That's how much we're investing. And then remember in this formula, after the p, always going to be an e, right? So whenever you see compounded continuously, it's going to be the principal times e. And now what's going to go in our exponent? Good. So our rate, 12%, we convert to a decimal. That's going to be 0.12. And then we have to multiply that by what? Good. So our time this time is 3 years. So we multiply that by 3. Okay, so we have 1,000 times e to the 0.12 times 3. Now again, if you want to put all that in the calculator together, that's fine. Just make sure your exponent is all grouped together. If you want to simplify the exponent first, that's fine too. So that would give us 0.12 times 3 in this case would be 0.36. And so we're doing 1,000 times e to the 0.36 power. Again, make sure you're using the E key on your calculator to do that. So what do we get? Good, right? So $1,433.33. Okay, and always round in money, always round to the 2 decimal places because that'll be the nearest cent. Any questions on how we got that? All right, now I want you to think back to the problems we did yesterday because we also did the exact same principal, time, and interest rate, but we did it with annually, we did it with monthly, and we did it with daily, right? So those were the 3 values that we used there. What do you notice about this value compared to those values that we got yesterday in that problem? It's more, right? Okay, so whenever you're compounding continuously, because it's a continuous compounding of interest, right, this is going to basically be the maximum amount that we could hit given these values, right? This principal, this interest rate, and that amount of time, this is kind of our max out point. Okay, whereas with annually, it's going to be a little bit less than if you were to do it on a monthly basis, and that's going to be a little bit less than if you did it on a daily basis. And now continuously is going to be the max. Okay. Now notice it's not a ton more, right? Because all of them were in the 1,400 range anyway, right? So this is only slightly more than if we had done it on a daily basis, but it is more, okay, than any of those other values. Any questions on that one? All right. So that's it for that section. So this is 4.3 now. So we're going to look at logarithmic functions. All right, so we're going to start off with a definition of what a logarithmic function actually is. Okay, so we're going to let a, so this is a variable a here, let a be a positive number with a not equal to 1. Okay, so our base can't be 1. The logarithmic functions with base a denoted this way, so this is log base a, is defined as if the base a log of x is equal to y, you can read this arrow as a then a to the y is equal to x. Okay, so this logarithmic equation right here is equivalent to this exponential equation right here. Now, the way we go from one to the other is we're taking the base, raising it to whatever power we have over here, and that's going to be equal to whatever value we have inside of our logarithm. So a to the y is equal to x. That's what we have right here. These two equations are equivalent to each other. And so what this tells us then is that this right here is the exponent to which the base a must be raised to give us that x value, right? So this a must be raised to this exponent to give us the x value inside. That's what this statement down here is saying. We're going to start out with some examples where we basically just convert these one way or another, right? Either given a log, convert it to exponential, or given an exponential equation, convert it to a logarithmic equation. Would anybody like more time on that slide? All right. So let's take a look at these. And I've actually got a typo here. So this should be a 4. So just make sure you change that. Okay, so the logarithmic and exponential forms are equivalent equations. So if one is true, then the other also has to be true. So what we want to do is we want to take this logarithmic equation right here. We're going to rewrite it in exponential form instead. All right. And so we're going to use what we did on the last slide to try to do that. So if we take a look at this first one, we have a base 10 log of 10,000 is equal to 4, right? So this right here is a true statement. We want to rewrite it, though, in its exponential form instead. So what would the exponential equation look like that would be equivalent to this equation here? Okay, good. So we're going to start with 10 to the 4th power. And then what should 10 to the 4th power be equal to then? Good, equals 10,000. And again, the easy way to do that is, right, we start with the base. We're going to raise it to whatever power we have over here. And that should be equal to whatever value we have inside of our logarithm. So we get 10 to the 4th power equal 1,000. This equation here now is equivalent to the logarithmic equation that we started with. Any questions on that one? All right. What about the next one? What would that equation look like? Okay, so we start with 2 to the 3rd power. And that should be equal to 8. Good. So just make sure you have the entire equation there, because we're taking 2 to the 3rd equals the 8. Any questions on that one now? All right, what about the exponential form for the next one? Good. We have 2 to the negative 3 power equals 1/8. Because again, our base is 2. We're going to raise it to the negative 3 power, and that should be equal to the 1/8 right there. All right, and then our last one here, what's that going to look like? Perfect. Okay, so we take 5 to the r power, and that should be equal to s. Because again, 5 to the r equals s now. Any questions on any of those and how we go from log form to exponential form? Anybody need more time on that one now? All right. Now we actually want to evaluate some logarithms. So we got base 10 log of 1,000. That's the first one. Right, now, you might be able to do these without doing a ton of work, just kind of reasoning through it. That's fine, right? But I'm going to actually do a little bit of work just to help us think through what we're actually doing here. So the first thing I'm going to do is I'm going to say, well, this is base 10 log of 1,000 equals some value that we don't know, right? So I'm just going to put an X there. Now, at that point, I want to rewrite this equation in exponential form. So what would the exponential form of this equation over here look like? Good. 10 to the x power is equal to 1,000. So what I'm trying to find now is I want to know what is this x value. So I need to know what's the exponent that I would raise 10 to that would give me 1,000. So what would that x value need to be this time? Good. X would have to be equal to 3 because 10 to the third power would equal 1,000, which means that this base 10 log of 1,000 is equal to 3 now. And again, if you don't want to have to do all this work every time, that's fine. If you can just say, oh yeah, 10 to what power equals 1,000, that needs to be a 3 because 10 to the third is 1,000. You can just get it that way, that's fine. Any questions on that one now? Okay. So again, I'm going to do the work again, but if you can do it without it, that's fine. So we have a base 2 log of 32 equals some value, I'll call it x. What's our exponential form this time? Good. 2 to the x equals 32. 2 to the x equals 32. And so now what we want to know is what would that exponent need to be so that when I raise 2 to that power, it gives me 32. Good. 2 to the fifth power is 32. So my x is 5, which means the base 2 log of 32 is equal to 5. Okay. Any questions there? All right, let's look at the next one now. This time, got a base 10 log 0.1 equals x. So what's my exponential form this time? Good, 10 to the x equals 0.1. Okay, so now I'm trying to figure out what would my exponent need to be here that I would end up with 0.1 when I do that exponent. Yes. Okay, so Sarah says -2. You're close, right? Okay, so in this case, it is going to definitely need to be a negative, right? Because I want to end up with a decimal. It should be -1. So what I'm going to do, what would 0.1 be as a fraction? Tell me that. 1/10, right? So this is like saying 10 to the x power equals 1 over 10. And so if I want to move this to the denominator, but to the first power, right, then my x value this time just needs to be -1. Because 10 to the -1, I would move that to the denominator, it would become 10 to the first power, and that would give me 1/10. So now I know over here, this log should just be equal to -1. Any questions on that one now? All right. So now this last one, we've got base 16 log of 4 equals x. So again, what's the exponential form for that going to look like? Good. So 16 to the x power equals 4. Now I'm trying to figure out what would this exponent need to be. So when I raise 16 to that power, it gives me 4. Okay. So Sarah, you're close, right? It is going to be fractional. Okay. And Kenneth, you got it. All right. So it is going to be the 1/2 power. Now let's think about why it's equals 1/2 here. What does it mean to raise something to the 1/2 power? It's a square root, right? And so in this case, when I take 16 to the 1/2, that's the same thing as taking the square root of 16, and the square root of 16 then would give us 4, right? And so that's why this one right here should actually be 1/2. Okay? How would you find x algebraically when it's in exponential form? So you're asking, make sure I've got your question right. If you were given an exponential equation, say this one, right, and it wasn't as obvious that that needed to be a square root, how would you then solve for x? Is that your question, German? We're going to look at those later. Basically, you're going to end up using logarithms to do that, to get rid of the x, to move the x out of the exponent. But we'll get to that a little bit later. And then sometimes you'll even have somewhere, it's not going to be a nice, pretty value. You'll have to use your calculator, and that's why we'll use logarithms to do that, and then we'll be able to put it in the calculator to solve. Okay, so yes, we're starting out with that. You can kind of reason through and kind of figure out what those values would need to be. But yeah, eventually we'll have somewhere, this base is a 3 and this is a 2, and there's no way to easily get from one to the other. And so we'll have to use some other algebraic processes to get there. Any other questions there? All right. So here's some of our properties of logarithms. Okay, so our first one here says that if we have a base a log of 1, that's always going to be equal to 0. And it does not matter what that base is, right? This is always going to be 0 because any number to the 0 power will always be equal to 1, right? And so this equation will always be true no matter what the base is. Our second property, again, no matter what this base is, this is always going to be equal to 1 because a to the first power will be equal to a, right? And so we know in this case, if these numbers match, that logarithm is always going to be equal to 1. And the next one, right, very similar. A to the x is equal to a to the x. Therefore, if we have the same numbers here, then we can just say that that logarithm is equal to whatever that exponent is right there. And then the last one's not as obvious, right? But it's just one of those properties we need to know that if we have a to the base a log of x, basically if this base and this base match, then we can just take whatever's inside that logarithm. That's going to be the value that we get there. Does anybody need more time on that slide? so let's take a look at these. First one here, we got a base 5 log of 1. So what should that be equal to? Good, right? So again, no matter what base we have there, if it's a 1 inside, it's always going to be 0 because anything to the 0 power is going to give us a 1 there. What about the base 5 log of 5? Good. And so this one should be equal to 1, because again, as long as these numbers match, that's always going to be 1, because this to the first power will give you that same number. All right. What about the third one here? Good. That one should be equal to 8. Again, as long as these numbers match, we can just look at our exponent, which is 8, because 5 to the 8th is equal to 5 to the 8th. And then this is that last case. Okay, and so what should this one be equal to? Good. So this one's just going to be 12, because as long as your base here and your base here match, those basically cancel each other out. And so we're just left with whatever's inside the logarithm, which gives us a 12 there. Any questions on those now? All right. So now I want to sketch a graph. So we've got a base 2 log of x. We could put this in Desmos, right? And a lot of the newer calculators will actually allow you to put just a base 2 log of x in your y equals and graph it. But I want to kind of work through this and think about what this graph's going to look like. So if you're not sure and you don't have access to a graphing tool that will graph it for you, what could we do instead? Make a table. Good. All right, so that's what I'm going to do here. I'm going to create a table, do some x and y values. So now we just want to take some values and actually substitute them in there and see what we get, right? So rewrite this as just y equals base 2 log of x, right? Okay, so this is the equation we're working with. So what do you want to do here as we create our table of values? Okay, so you want to plug into x. All right, so tell me some x values you would like to check then. Okay, 1. All right. Check 1. So if we do that over here, that gives us y equals base 2 log of 1. Well, what's the base 2 log of 1 going to be equal to? Good. All right, so this right here, no matter what the base is, if there's a 1 inside, that should be equal to 0. So now we've got a point at 1, 0. All right. Give me another value you want to check. 2. Okay. Y equals base 2 log of 2. So what should the base 2 log of 2 be equal to? Good, right? That's just going to give us 1, because again, as long as those numbers match, we should just get a 1 there. 2 1 as another point. What other values you want to check? 0, okay. So if we plug in 0, think about that. So y equals base 2 log of 0. What's the base 2 log of 0 going to do? Exactly, right? So the fact that it took you guys so long to kind of think through, well, what is that going to be, right? There is no value because what we're trying to figure out is 2 to what power would give us 0, right? If we put 0 over here, we're automatically going to get what? 1, right? Okay, so 2 to the 0 power would actually be equal to 1, so that's not going to work, right? And so there is no value that we could put here, so this is actually going to be undefined. Because there's no exponent that I could put here that 2 to that power would give me 0. So at 0, this function is actually undefined. Okay. What other values would you like to check? -1? Okay. Let's try that. So we've got base 2 log of -1 equals what? So again, the question is there a number I could put over here that if I do 2 to that power, I will end up with -1? And so in this case, it's going to be just like the 0, right? It's going to be undefined because nothing that I can raise to to give me -1, right? Because 2 to any power, even if I make this a negative value over here, right, that's just going to give me fractions because I'm going to move that 2 to the denominator, right? So there's nothing that I can raise 2 to give me a negative, right? Which means if I choose -2 or -3 or any other value over here in the negatives, it's going to be the same thing because I can't raise 2 to some power to give me a negative value. Okay? Now that means we've only got 2 clearly defined points right now, right? So we probably need a little bit more. We already said all the negatives are going to be undefined, so there's really no point in checking any more of those. So what other values can we check? All right, so I see 3, I see 5. All right, so let's check 3 next. So we've got y equals base 2 log of 3. So that's 2 to what power equals 3? Anybody have any ideas? Okay, yeah, right. It's not an easy one, right? Okay, it's going to be a decimal value for sure, because 2 to the first power would be 2, so it has to be like 2 to the 1 point something. Okay, that would give us 3. This is not a good value to check, just because since we're doing logarithms, we really want a nice, easy value to plot over here. What could I put in here instead that I could find a nice value on the other side? 4, right? So let's do that instead. Okay, so just kind of keep that in mind when you're doing these logarithms. If you're making a table of values, try to use numbers that are going to be easier to figure out the exponents, right? Because now 2 to what power would give us 4? 2, right? And so that log would be equal to 2. And so now we have a point at 4, 2. Right? Same thing, somebody suggested looking at 5. 5's not going to be easy because 2 to what power gives us 5? There's no clear answer there, right? So what value could we check instead where we could get a nice exponent? 8 would be the next one, right? Because now y equals the base 2 log of 8. Now this exponent would need to be what? 3, right? So that's probably a good list of values, right? Because now we have these 4 points that we can graph and then get an idea of what the graph's going to look like. So do that. So our first point, got a point at 1, 0. Over 1 to the right, but on the x-axis. That's where we go. And we're going to go over to the right and up 1. So right 2, up 1, point there. Right 4, up 2. Point here. And I probably should have put these a little closer together. 5, 6, 7, and 8. Up 3. I'll put us somewhere in here now. All right, so just looking at what we have so far, right, we've got something that looks like this right here, almost like your square root function, right? If you remember doing those, remember the square root would start at 0, 0 instead, okay, but it kind of has that shape to it over here on this side. Now the question is, does it actually stop here, or are there more values that we're still missing, okay? So what we need to think about now is, we said 0 wouldn't work, right? But are there any values now between 0 and 1 that could work, where we could get an actual value? So what values could we check now between 0 and 1 to see if we have any other points there? Okay, 1/2. Set 1/2. That's y equals the base 2 log of 1/2. Well, 2 to the what power would give us 1/2? Good, Asbel. So -1, right? Because in this case, right, if we take 2 to the -1 power, negative exponents move to the denominator, right? And so that's going to give us that 2 in the denominator now. So this would actually be a value of -1. So what that tells us is there actually is a point at 1/2, -1. So we go over to 1/2, we go down to -1. There's actually going to be a point right here now. What's another fractional value between 0 and 1 that we could check here? Okay, 1/4, because the base 2 log of 1/4 would be equal to what? We're saying 2 to what power would give us 1/4? Good, right? -2. Because 2 squared would be 4, but because it's negative, we move it to the denominator. So that gives us 1/4. So this value here would be a -2. So now we know there's also a point at 1/4, right? It's getting even closer to the y-axis, and then down here at -2. So what's happening here, right? So what do you notice? We have this piece of our graph up here, but we do have some points down here in the negatives now. So what's actually going to happen as I get closer and closer and closer to 0? There's a vertical asymptote. Good, right? So we have an actual vertical asymptote at x equals 0 along the y-axis here. And so our graph do something like this. And that'll be true of all of your logarithmic functions, regardless of what the base is. They're all going to have some things in common. One thing they're going to have in common is that they're going to go through this 0.10, because anything to the 0 power is going to give us 1, right? And so we know in this case, you should go through that point. As long as it's just a basic logarithmic equation, base 3, base 4, base 10, doesn't matter. You're always going to have this vertical asymptote at 0, because 0 is always going to be undefined, and so are all the negative values, right? So we're always going to have that asymptote at 0, again, as long as it's just a basic logarithmic function, no transformations or anything. And then it's always going to be going up and to the right like that, so long, again, as you don't have transformations where you're doing reflections or anything. So always be the basic shape of a logarithmic function, regardless of what the base is there. Yes, sir.
How do you use the graphing calculator to find the logarithmic function?
So that's a good question. You can do a base 10 log, and we'll get to this later because I want to make sure that I cover what a base 10 log actually looks like and how to put it in a calculator. Some of your newer calculators, you can actually change what that base is if you go into your math menu, but a lot of the older ones, like my TI-83, won't do it. Even the early TI-84s, you can't do it. And so we have a formula that we can use that allow us to change the base that'll then allow us to put it in the calculator. So we're going to get there. So if you can just hang on to that for now. Yeah, because I don't want to.
I was just wondering if I needed to know that for the homework or anything.
Not yet, okay, but it is coming, right? So I'll definitely point that out when we get to it. But there is a way to put that in there. We just need a formula to do it.
All right, thank you.
Yep. Any other questions there? All right, now, here's the next thing I want you to think about. I want you to think about the fact that we can change these functions into exponential functions, right? And so there is some relationship now between the logarithmic function and the exponential function. We need to figure out what that relationship is. Well, let's just say, for instance, right, if this was my base, 2, and I had 2 to the x power instead, right? Instead of a logarithmic function, what if it was just y equals 2 to the x? What would that function look like? It's a J-shaped curve, right? Okay, we have a base that's bigger than 1 raised to some x power, right? So it's going to be a J-shaped curve. We know in that case it should go through what point? Okay, 1 along the y-axis, right? So 0, 1, that point right there, J-shaped curve, and we're going to have an asymptote where? Good, 0, specifically y equals 0, because it's going to be a horizontal asymptote this time, right? So I'm just going to sketch this in here. I'm going to do it as a dashed line so it's clear, right? This is not the function we were graphing before, right? But this is this function down here now. Okay, the y equals 2 to the x power. Now, do you notice anything about those graphs? Any relationship there? Okay, so it does look like some kind of reflection, right? So if you look at it, it looks like there's a reflection there. Now, if you did a reflection over the x-axis, though, what that would give us is this whole thing would just get flipped down here, and you'd have something more like this, right? So it's not exactly a reflection over the x-axis. What kind of reflection is it? What are we actually reflecting over here? Okay, so y equals 0, so that would be this axis, right? So if we did this, well, y equals 0 would be the same thing as this, right? So y equals x, right? So the equation y equals x, that would be a diagonal line with a slope of 1 that would go through the point 0, 0, because that would be our y-intercept. Okay, so this is y equals x right here. And so if you look, if I were to take this y equals 2 to the x and I reflect it over that line, it's actually going to give me this graph that we just got here for the base 2 log of x. Well, do you remember what we said about reflections over the line y equals x and what that relationship is between those two graphs now? So not slant asymptote, right? So be careful there, because a slant asymptote would mean that our graph is actually approaching that line, right? And it's not in this case. It's just saying that this equation is a reflection over that line to give us this equation down here. But if we reflect over the line y equals x, and that gives us the other equation, what do we say about those two functions? Inverses. Good, right? So these two equations now are going to be inverses of each other. So if we think about this, I want to change this now to exponential form. What would be the exponential form of this original equation here? So almost, right? So the base is 2, but we want to raise it to what power? 2 to the y is equal to x, right? So the exponential form of the original logarithmic equation would look like this right here. But then how do we find an inverse of a function? Okay, so plug y for x and plug x for y, right? So we switch the x and y values. So if I switch my x and y here, what's that going to give us? And I think Kenneth's got it there, right? So we're going to switch this to an x, which is going to give us 2 to the x. We're going to switch the x to a y, which gives us the y. And so this right here now becomes our inverse for that original logarithmic function. So again, we can go from log form to exponential form. We can switch our x and y, which gives us the inverse. And so that n actually becomes this exponential function down here. And we can see that graphically because it's a reflection over the line y equals x. So the key there is logarithmic functions and exponential functions are inverses of each other. And the reason that's important is because now when we go to start solving equations later, since they're inverses, we'll be able to actually use logarithms to undo exponents, or use exponents to undo logarithms, right? So because they're inverses, we can help use them to cancel each other out and solve equations now. Any questions there? All right. That's it for today. Again, don't forget the test is due by midnight tonight. If you have not submitted that already, let me know if you have any issues getting it uploaded. Have a good afternoon, and I will see you tomorrow. Naomi, let me double check and make sure I've got you.